Yeah, well, it's one of the bits of feedback I gave quite a lot to the university was there's this lack of a feedback cycle, right, for supervisors to, or even the course, right? So at Sheffield, at my old uni, once, just before term starts, the lecturer in charge of a course gets all the TAs together, talks about what's happening and that kind of thing. Nothing like that happens at Cambridge.
They do have one session.
They do an introduction to supervision, but it's not. So there's no feedback between the lecturer and the people who are actually teaching the students on the course. Right? That's because the colleges organises supervisions, department organises the lecturers. So the lecturers don't have any way of knowing who supervises their course. Massive gap. Yeah, exactly.
All right. Welcome everyone to this afternoon session of CPP, creatively titled Isabel, PVS. And in the session we really have everything. We start with a remote presentation, then we will have a distinguished paper and also a regular paper. But first off, Lauren White from NASA will present her work together with Laura Titolo, J. Tanner Slagel, and Cesar Munoz on a temporal differential dynamic logic formal embedding. Lauren, please go ahead. I hope we can hear you. Oh, Lauren, you were not able to hear me, but I introduced you already, so you can just go ahead. We cannot hear you yet. So. What should I ask her?
Is the audio working?
Yeah, now it's working.
Okay, perfect. I will start and I'll go into presentation mode. I won't be able to see the screen anymore, so just let me know if you need me to get out of that. All right. Thank you so much for allowing me to present remotely. I and my colleagues from NASA Langley here in Virginia, where I currently am, are excited to present this finalized work on temporal differential dynamic formal embedding. So just a brief introduction. I'm going to talk about the interactive theorem prover that we formalized our work in, which is PVS. And then I'll also talk about what is the differential temporal dynamic logic, or DTL2, and a little bit of the specifics of putting this logic into a theorem prover. So the resulting embedding of DTL2 is actually an extension of a previous work which formalized the logic differential dynamic logic, or DL, in PVS. And this work resulted in an embedding that we call platypus. And what DL and DTL and these two logics tackle is reasoning about something called hybrid programs. So a little bit about PVS. So PVS was developed by SRI International. It's an interactive theorem prover working on higher order logic, completely typed with dependent types. The nice thing about utilizing PVS is that you can write customizable tactics and strategies for the interactive theorem prover. And there's also a Visual Studio Code extension. And it's sort of the favorite interactive theorem prover used by NASA, especially NASA Langley, has been used for many, many years. So the resulting effort is this massive library called NASAlib that's publicly available and has tons of, this work, and it's the predecessor to this work, as well as, graph theory, matrix theory, sort of abstract algebra, lots of different mathematical and computer science type concepts. So in PVS, what we want to reason about is something called hybrid systems. So hybrid systems are important to the work of me and my colleagues in order to verify properties about systems that contain continuous and discrete behavior. So this is important in the field of like aerospace and verifying safety properties because systems such as, a like flight vehicle or multiple flight vehicles, a system of flight vehicles can all be represented by these types of hybrid systems. And the previous effort finalized a specification and a reasoning formally in PVS about these hybrid systems, aptly named platypus because platypus is like the hybrid animal. So what are hybrid systems? Well, they can be thought of as formally as hybrid programs where you have sort of discrete assignments that would be the discrete component, and then differential equations, which would represent the continuous component of that system. And so in platypus and this DTL2 extension, which extends platypus, these systems of differential equations and these discrete assignments are all formalized, and ways of combining them by union or sequence, like run one hybrid program, then run the next, or finite but unknown number of repetitions, represented by this little star right here, and the test. So testing whether some property is satisfied at the end of a run of a program. And so just to kind of ground ourselves of how would you write a program that does something that I'm interested in proving properties about? So here we have a very, very simple cruise control. So what basically this program is doing is it consists of two components that are checked and run, an undetermined amount of times. But in that test, the program basically checks, okay, is this value v less than v0? Then set my derivative of v equal to some value, otherwise set it to a different value. And so this is kind of a rudimentary cruise control where if you're below a velocity, you could accelerate, and then if you're above that velocity, you decelerate. So you're kind of sawtoothing between a target velocity v0. Okay, so a little bit about DL and the DTL logics. So what DTL and DL do are they're logics that have semantics and rules. So the semantics of DL takes these things called environments, which are basically the state of a program at a given time. And so if you wanted to know what like the xi state variable is doing, then you would just plug in I into this, and then you would get the value for that given time. So what DL does is relates input and outputs of a program. But for safety properties of systems, maybe something in between is happening that we want to be able to capture. So imagine, for instance, you want to say something along the lines of, for all time, my airplane stays within a given zone, right? So it doesn't leave and go into like a no-fly zone. Well, if you're only reasoning on initial and end states, there could be some rogue behaviors where it goes out, comes back in, and that's not captured. So what DTL2, the logic, does is tries to reason on intermediate states by introducing not just inputs and outputs, but reasoning the semantics of a trace. So traces are lists of values. They can be like discrete values, for example, like T0 to T1 to T2. But you can actually also reason on the continuous solution of, like, let's say, the differential equation that's part of your system. And you can reason on that differential equation solution on a finite interval of time, or even just let it run out towards infinity. Okay? And if a program fails for a given state, you can also have an error. Perfect. So what DL does is, if you're reasoning about inputs and output states, you can reason about all runs of an input and output. So imagine you have some initial set, all runs of the program in that set, and you look at all the sets of the output state. Then you want to check if maybe they satisfy some P, right? And for the sum runs operator, you can say, like, does some run where you start an initial set reach some output state? And for DPL2, because it's built off of DL, you can reason about all runs and some runs of a program on their traces, so not just inputs and outputs, but all the intermediate states as well. And how we reason about those intermediate states is with the globally and eventually operators. So these are temporal operators that basically check whether the tail of a trace satisfies some property. So the tail meaning take somewhere in the middle of the trace, cut it, start at that point, and then continue your trace on to the end. And those tails are called suffixes. So the globally property would mean for all suffixes that some property is true, and then eventually means there is some suffix that the property is true. Okay, and so now that we have sort of what objects these programs are going to be reasoned on, you can see in this formalization, so this is PVS, so how we define elements of a trace list. So these are deeply embedded. We have the differential equation that goes from 0 to infinity in time, differential equation solutions that are only on finite time, and then the discrete, like one environment or state in this case. And what we want to reason on are traces that don't have an error in the middle, because if you had an error, why would you continue going? So those shouldn't be part of the semantics. And then also an infinite one where you have temporally, like time going from 0 to infinity. You wouldn't want any other element after that in your trace list, because you're going from 0 to infinity. So we can restrict and we can impose these sort of subsets of traces and reason on those. And then when we define how the semantics are satisfied, it's just basically for any input and output, you would have some property be satisfied. Here, the assignment, basically that your output follows the assignment rules. Perfect. So why would you want to reason about intermediate states? I kind of talked about it a little bit, but here's a concrete example of something that you can prove in DL. so the core logic, and then something that the temporal extension kind of shines more light on. So we have this hybrid program where you have a derivative, so differential equation, x prime equals 6, and then followed by the program where you assign that value to its floor. So it's true that for all runs of the normal, like core DL, that since you're only reasoning about output states, you would always end with the floor, like you can't stop anywhere in the middle of this program. And so therefore, all of the outputs would be integers. But we know that there's some intermediate state where that's not true. So the second property is just that there's some run that eventually the trace will take on a non-integer value, right? And for us, this is where we differ from the DTL2 logic that has already been sort of published and was specified by Jean-Baptiste and André Platzer in their paper. We actually eliminate the possibility, we don't allow for the possibility of error traces to belong to the semantics. And the reason why is that if we end in an error, that means that the actual hybrid program wasn't satisfied. So, for example, the semantics, if you allow for errors in this program where we assign x to be 0, then if x is less than 10, add 1 to it and keep repeating that. And here we have this final check, is x greater than or equal to 10? So it's sort of a reachability property that we want to happen, where we don't want a program to just be killed prematurely. And so by eliminating the error traces, we kind of we can write programs that force conditions of reachability, which is important in differential equations, since if you wanted to say like all runs of a program reaches a certain state and it's defined by a differential equation, the differential equation can actually just end at any moment. And so making statements about all runs of the program where you can't specify that the time has run long enough is very difficult without elimination of these error traces. What eliminating error traces does is actually changes the rules slightly. So in DTL2, there's a rule schema where this double bar is implication in both directions. So without errors, the implications in the original paper that we were working off of for the embedding, some of those implications didn't go both ways. So we have edited the rules slightly so that they go both ways. And these rules are used in proofs. So you have these rules specified, they're proven formally inside the theorem prover, and then they can actually be utilized when you're actually trying to prove something. So here's an example. Here's that example that we saw earlier, where you have some runs, like a sum run will eventually get you a non-integer value for the sequence where x prime equals 6, and then you assign x to the floor of its value. So this says eventually you're not an integer, and then the normal DL all runs where you do end in an integer. And so these proof rules, they do replacements to make a more simplified statement in order to get down to, instead of a sequence of hybrid programs, like it breaks it up into one hybrid program and then the other. And so the simplification gets you to a point where either you can prove it in its totality with these proof rules, or you get a statement that's hopefully trivially true. Perfect. And yeah, so that in total is kind of our what our work entailed. And I guess to kind of very simply compare it to other works, there's a implementation of DL in another theorem prover called Kimara X. And one of the core distinctions between the PVS embedding of DL and DTL versus Kimara X is that you can actually reason about instantiations of differential equations that aren't like x prime equals a function. You can actually abstractify it to x prime is some function that satisfies certain properties. So you can prove sort of more general properties about not just one differential equation, but a family of differential equations, for instance. Looking forward to future work to allow us to prove things in more general senses, like black box type verification. Oh.
Is the mic on? Are there any questions? You have to come to the mic here. And please say your name and affiliation.
Hello, I'm Ekaterina Komendanskaya from Southampton University. I have a question how you do differential equation solving in PVS, because Kimara depends on Mathematica and other similar tools to do crunching of differential equations, and I'm very curious how PVS can do it.
Yes, so there is so basically the idea is the goal of using DL is to hopefully avoid solving differential equations if you can, because very quickly it becomes nearly impossible to solve a differential equation. So ideally you would use proof rules or things like that, but there are theorems built into PVS that deal with ODEs. So we have an ODE library that says, for example, up to quadratic differential equations, we have, a theorem tactic called DL solve, where it will actually do a direct replacement instead of going to Mathematica or something of that nature. But we are looking for sort of future work as to how do we integrate those kinds of tools, because it does become sometimes important to just solve the thing. But yes, right now it's not a capability, but there are some differential equation theory to help.
Can I just react to this? I think it's very valuable that you do this within PVS without going to Mathematica, because for me, it's actually a weakness of Kimara. Then you outsource computation that you want to trust to some other programming language that you may not trust. So it's just a big round of applause that you do it in PVS.
Yeah, there is some theory, and the idea of not going to another program is a choice of ours, because we want that trust and that formal verification to happen in as many layers as we possibly can.
Okay, thank you.
Thank you.
Are there other questions? I have a question as well. So Dmitry Titolo, University of Copenhagen. So for the modeling, for your modeling of the error states, I wonder whether you sometimes encounter the situation where the system should be able to recover from an error. And so I'm thinking in particular of a plane that usually should fly in a safe region, but then maybe there is a semi-safe region which it could enter for a short period of time, and then it should quickly get out of it. So how do you model such situations?
Yeah, so the idea would be you can create those kind of buffers. So for example, we have a current project that we're working on that would, in a certain region, the differential equation is sort of a black box, meaning like a pilot has active control. The differential equation is just some general, x prime equals f of x, right? Only you can do multiple dimensions. And then outside of that region, we have a banded region that kind of gives, let's say, an epsilon buffer around the boundary. And in that region, we can have a control switch. It's sort of like you're green, and then you're yellow, and then you're red, right? And so in the yellow region, an automated control would take over and then turn back to the safe region. So there's ways of integrating that in order to specify that time runs for long enough. And if you get into a red region, you can say, if red, turn off. This would be very extreme, but in the case of, let's say, a drone where there's no pilot, to kind of take the manual reins, and it's, flying with some sort of AI program or machine learning program to optimize a flight path. If it goes into a no-fly zone, we have current capabilities hardware-wise where if it goes into that zone, the battery just shuts off and it falls out of the sky.
Thank you. Sounds a bit dangerous, maybe, but okay.
Yes. Well, the goal in the red zone would be that the red zone begins very far away from where people are. So a lot of our applications currently are, in more remote areas where dropping the drone would only pose a monetary cost as opposed to, a hazard to humans. But other sort of avenues are being dealt with as things sort of progress.
Makes sense. Let me ask you another thing, unless there is a question that shows up. Now, I would like to ask about the real-time aspect and whether you sometimes feel the desire to express real-time properties, like the differential equation should behave like that in the next hour.
Yes. So this is, for now, because of the requirements in order to actually verify, this is sort of a design time verification, but actual runtime verification is an avenue that we're looking into as far as in runtime, how quickly and how often can proofs automatically execute and show that, yes, in the next hour you will be safe, and what is the time buffer on things like that. So there is some effort in the future to kind of optimize this automated portion of the theorem proving and automated portion of sort of how the system is behaving as far as updates go.
Thank you. And let's thank Lauren again.
Yes, thank you so much. And thank you for allowing me to, be here virtually.
Thank you.